Alright, right now I'm heading to the gym to pump some iron. Let's hear from Professor Fozon and what he has to say about constant velocity. Hi, my name is Fozon Amjad, and I'm a professor of physics at Ryan Burns University. To understand constant velocity, we must understand the term velocity itself. We are familiar with the term speed from our day or night interactions. You know what's up. Speed is the rate of change. Speed is the rate of change of distance over time. To calculate the average speed of an object, we divide the total distance by the total non-zero time interval. To calculate the instantaneous speed, we take the limit of the average speed as time approaches zero. And for you calculus folks out there, I mean just simply taking the derivative of distance with respect to time. Now velocity is a little more different, but the concept is relatively the same. Velocity measures the rate of change of displacement with time, keyword being displacement. Unlike speed, which is a scalar, meaning it simply has a magnitude, velocity is a vector, with both a magnitude and a direction tied to it. Calculating instantaneous velocity is simply taking the limit of the average velocity as the non-zero time interval approaches zero. For something to be constant velocity, they must maintain the same difference in position in the same interval of time. In a really weird way, I'm basically saying that by graphing the antiderivative of the numerical value of your velocity, you will attain a linear function, and by taking the integral, you'll attain the displacement. By taking the derivative of the constant velocity function, you will attain a zero acceleration, because the slope of the velocity versus time graph is zero. Constant velocity can describe the motion of an object that is still. Look at that tree. Look at that wood. It's in constant velocity. If we construct a force diagram of this tree, we find that the net forces acting on it is zero. However, constant velocity can also describe objects that are also in motion. Let's take a look at that. Alright, right now I'm at the Woodbridge Community Center. Hopefully they'll let me take the footage I need for this physics project. So here's the subject roller skating in the rink, acting like he's some cool dude. The friction force is so small that we can consider it negligible. The only forces acting on the system are the force of gravity and the normal force, which cancel out each other to achieve a net force of zero. When we look at the position versus time graph, we see a linear function, and when we take the derivative to get the velocity versus time graph, we get a zero slope graph, meaning that our subject, who's acting like some cool dude, is going through constant velocity with zero, and I mean zero acceleration. Acceleration is the rate of change of velocity, which again, for those cow folks out there, is the derivative of velocity. Now that we learned in order for something to be in constant velocity, the position should change at a constant or otherwise linear rate. Well, by using the same logic, if the velocity of the subject changes at a constant linear rate, then the acceleration is a constant number. If we take the antiderivative of a constant acceleration formula, we will attain a linear velocity function. If we take the antiderivative of a linear velocity function, we attain a parabolic position function because of the reverse power rule. In the video that will be shown, my father attempts to change the velocity of the car at a constant rate, hereby simulating constant acceleration. Within this situation, we have to account for multiple forces that are acting on the system. We have the force of gravity, as well as the normal force to balance it out. In the negative horizontal direction, to be more specific, is the friction force, while in the positive horizontal direction is the applied force. The applied force is more than the friction force. Therefore, the net force is not zero. We have a net force. According to Newton's second law, since there is a net force and we have a mass, we ultimately have an acceleration. Now, we ultimately do not make this conclusion. We have to account for the entire system. There's always a system, right? However, within this case, we've accounted for most variables. When we look at the position versus time graph, we see a parabolic relationship. Howdy. When we take the derivative to get the velocity, we attain a linear graph, which is suggesting that the velocity is changing at a constant linear rate, which is suggesting that we have constant, and I mean constant, acceleration. Alright, I'm going to be meeting the rest of my boys at the soccer field. Tune in and let's see what Professor Fozon has to say about projectile motion.
Oh yeah, projectile motion!
What it be, what it do. Professor Fozon back with another physics review. Personally, projectile motion is one of my favorite topics because it combines two distinct topics that we've previously learned. Constant acceleration and constant velocity. But how does this work? Well, we have to break the projectile into two parts. Well, wait a second, hold up. What the hell is a projectile? Well, first off, a projectile is any object whose acceleration is due to gravity alone, and it embarks on a journey known as its trajectory. We break up the instantaneous vectors of the projectile into two parts, its horizontal and its vertical components. There is no acceleration in the horizontal direction, meaning that its initial horizontal velocity it starts off with is the final horizontal velocity it ends with before hitting the ground. To calculate the displacement in the horizontal direction, we simply take the derivative of the constant velocity and attain a linear function, meaning the rate of change of horizontal displacement is constant. Now, the vertical component is very different because we are dealing with constant acceleration in the negative, aka downwards, y direction. This means that the rate of change of velocity will be a negative linear function. Simultaneously, the displacement in the y direction will be downwards parabolic, because when we take the antiderivative of a linear function, we attain a parabolic function. Let's see the example of a soccer ball with my homies, and they will illustrate how they play some ball. That was so cringy, wasn't it?
Go!
Oh, that was perfect. That is perfect. The force diagram is very simple for the ball in this situation. The only force acting on the ball besides air resistance, which we're not accounting for because, you know, we're the cool kids, right, is the force of gravity, which is in the downwards direction. The functions for horizontal and vertical components will differ ultimately because in the x direction, all forces are balanced, meaning there's no acceleration. The constant velocity allows the ball to move the same amount of distance in the same interval of time. Now, note that this is the horizontal displacement. On the other hand, the forces in the y direction are not balanced, meaning that there is a net force. The constant acceleration of gravity ensures that the velocity changes the same amount in the same interval of time, and the change in the position in the y direction specifically, will embark on a parabolic change. All in all, projectile motion is so cool to combine both the aspects of constant velocity and constant acceleration, two significant vectors in physics that describe the motion and physics of our world ultimately. A wise man once told me, it's not the length of the vector that counts, it's how you apply the force. I guess that's enough physics for me today. Thank you for watching.